All right, Henry, try your microphone again. Let's see if that works.
Can you hear me now?
I can hear you now.
Alright.
How are you doing?
I'm doing fine. How are you?
I'm doing well. It's awesome that we after this week we have a kind of have like next week off because Monday and Tuesday are only school days, but we don't have any sessions or anything. So it's like almost having a whole week off. Yay. Any questions up until now, Henry?
Not that I can think of right now.
All right. I'm gonna wait one more minute and see if Caleb shows up. He's usually here. We'll see if he shows up before 4 o'clock before we start. How's the weather up by you guys? All right, it is 4 o'clock. I am going to begin. I forget. Oh, last week we were talking about we're talking about the second derivative test, which gives us concavity. First thing I wanted to talk about today is um, the next 2 weeks. If you take a look at the pace chart for this week, you'll see that this is week number 12, and it is kind of a longer week. It continues on, so we have Monday, Tuesday, Wednesday, Thursday, Friday, and then next Monday and Tuesday, all are considered week number 12. So everything that we're going to go through today will be on week number 12. So next week, there is no main lesson since there won't be anything new next week. It's just and we call it a long week, but it's really a regular week with just 2 extra days. You guys have off on Wednesday, Thursday, and Friday. So next week is only 2 days. If you get all of your material done this week, you don't have to do anything next week, which is awesome. All right. We do have some things to work through this week. Let's see. Oh, man, I don't have any review problems from last week? Huh. Interesting. Must not have looked at my slides carefully enough. All right. Let me see if I'm just going to go back. I'm going to go to a blank screen. I'm going to pull out my calculus book. 1 second here. Because I want to put a problem using the first and second derivative test. Gotta find one here. I don't want to put up a problem that doesn't work out. Let's see here. Just paging through. See if I can find a decent one. Let's see here. All right. Let's try. That doesn't help us. That doesn't help us. All right, here we go. First and second derivative test. Let's go find a halfway decent one. All right, so I've got, let's go 4x to the third plus 21x squared plus 36x minus 20. And I want to know where it's increasing, decreasing, concave up, concave down. I want to know if there's any inflection point. So basically everything that we've been working on for the last 2 weeks, okay? So the first thing that we really want to do when we're dealing with a problem like this is we always want to do the first derivative test. First derivative test gives us where it's increasing and decreasing. Second derivative test gives us concavity. Okay, so the first thing I'm going to do is I'm going to take the first derivative. First derivative of this thing is going to be 12x squared plus 42x plus 36. And since I'm going to want to factor this thing, 1 second here, I have to sneeze. Must be allergic to calculus. All right, so then I'm going to probably, let's see here, can I factor out a 12 here? It doesn't seem like 12 goes into 42. So let's factor out a 6. So that's going to give me 2x squared plus 7x plus 6. And then I'm going to factor that because I want to know what my intervals are going to be. Okay, so if I factor this, let's see here, so I get a 12 on top. So this is going to be 2x, 2x. 6 is still in front. Let's see here, 5 and, let's see here, 4 and 3. And I'm going to divide a 2 out of this one, so it's going to be x plus 2 and 2x plus 3. So I have it factored. So that means negative 2 and 3 halves are going to be my, well, they're not my intervals, but where my maximum is going to occur. So I'm just going to go negative infinity to negative 2 would be my first interval. From negative 2 to 3 halves is my second interval. And 3 halves to infinity is my last interval. So then I need to know where is it positive and negative. Okay, so I'm going to take like negative 10 here. If I plug it in here, let's see, my function was 6, then 2x, nope, it was x plus 2, and 2x minus 3. So if I put 10 in here, so this is always going to be positive. If I put negative 10 in here, that's negative. If I put negative 10 in here, that's negative. Positive, negative, negative, that's positive. So I know it's increasing from negative infinity to negative 2. And then I'm going to take the value 0. So if I put 0 in here, that's positive. That's positive. That's going to be negative. So that's going to be a negative. So it's decreasing. How is it 2x minus 3? Oh, that's 2x plus 3. Sorry. 2x plus 3. So it's going to be negative 3 halves. Oh, boy. All right. So that's going to be negative 3 halves. Did I do it right now? Yeah, I think it's going to be a positive there. So it's going to be negative 3 halves. So now my whole interval is wrong. Well, I suppose I can just put negative 3 halves there because that's going to be in there. And negative 3 halves. Is that better, Caleb? Does that look better? All right. So now I have to take a value between negative 2 and negative 3 halves. There's not a whole lot of values in there, is there? Let's see. So negative 2 and negative 1.5. So I can take negative 1.75 if I want to. So that would be positive here. Negative 1.75 plus 2, that's positive. Negative 1.75, that's going to be negative. So it still is negative there. So it's decreasing. And then let's just take 0 here. So if I put 0 in here, that's positive, positive, negative. So, yeah, because if I put 0 there, that would be negative. Oh, no, because that was a positive here, wasn't it? Oh, shoot, I got to change this too. All right, so that's going to be positive. So it's increasing. Phew. So now I've got where it's increasing, decreasing. So if it's increasing and then decreases, I know there's going to be a max, a negative 2, and a min at x equals negative 3 halves. Then in order to find the second derivative gives us concavity. So I would just take the second derivative here. So my second derivative is 24x plus 42. Again, I'm going to factor out a 6. So that gives me 4x plus 7, I think. So I only have one interval. Well, I have 2 intervals. That's going to be negative 7/4. So I have negative infinity to negative 7/4. And negative 7/4 to positive infinity. All right, so if I take a value in here, well, let's just take negative 10. If I put negative 10 in here, that's going to be negative. So I know it's concave down. If I take a value in here, let's take 0. Put 0 in here, that gives me positive. It's concave up. So I know there's an inflection point at -7/4 because it's changing concavity. Concave down to concave up means there's an inflection point. So this is basically everything we did for the last 2 weeks. Any questions on any of that stuff? All right. Whew. That was a quick adding a adding a review problem on there. Okay, so now I got to go back to my slides here. All right. This week we're going to be talking about optimization with calculus. Okay, so this is a lot of where problems, that we use the calculus that we've learned. So when we're dealing with these are all going to be word problems. It says first you want to do is you want to read it through and you want to understand the problem. Then you want to develop a mathematical problem for it. Graph the function if you can. Most of the times I don't graph the function. It really doesn't make any difference. Identify the critical points and endpoints and solve the equation. Okay, so for example, here is an optimization problem. It says an open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? What is the resulting maximum volume? All right, so when I used to teach face-to-face, I used to have the kids, I used to bring in a piece of paper and I'd have the kids cut out a 1-inch square here. So if this was 20 inches and I cut out a 1-inch square, then it would be 18, right? Because you would have the 1-inch square here and the 1-inch square here, so this would be 18. If this was 25 and we cut out a 1-inch square on both of these, this would be 23. So then we cut out a 2-inch square. Well, if we did that, what would the volume be? Well, the volume, so x is really our h value, right? However big we cut this square, that's going to be the height of the box. So we would say that would be 1, and then my width would be, did we say 18? And my length would be 25 minus 2, which would be 23. So if I wanted to find the volume, if I cut out a 1-inch square, my volume would be 18 times 23 times 1. Or, calculator this week, yay, it would be, the volume would be 414 inches cubed. Okay, so now let's say we cut out a 2-inch square. So now I'm cutting out 2 inches on each. Well, if I cut out 2 inches, now my width is not going to be 20, it's not going to be 18, it's going to be 16. And then my length, well, it's not going to be 25, it's not going to be 23. I'm cutting out 2 inches on each length. So that's 25 minus 2, so that would be, what is that, 21? So now my dimensions would be 2 times 16 times 21. So let's go 2 times 16 times 21, and that would give me my volume now would be 672. So a 2-inch, the height, cutting out 2-inch squares would be much better, right? I get a better volume. But we don't want to do this for every single value, because usually we're going to end up, with, we could do hundreds and hundreds of them to figure out what the maximum volume is. So what we really want to do is we want to set up an equation. Our equation is going to be, this is going to be x, and our length is going to be 25 minus 2x, because whatever x is, if it's 2, then it would be 25 minus 2, that would be the length, and 20 minus 2x. So here is a generic function for finding the volume. So now this is volume, all right? So I want to multiply this out. So volume is equal to, well, if I multiply x through here, I end up with 25x minus 2x squared. I still have to multiply that by 20 minus 2x, right? So that means I have to do a little bit of math here. So volume is equal to, So I haven't done any calculus yet, right? I'm just working this problem through. So I've got 25 times 20, so that's going to be 500x. And then all I'm doing is I'm just foiling here. So this is going to be negative 50x squared. And I'm going to multiply here, so that gives me negative 40x squared, and negative 2x squared times negative 2 is going to be positive 4x to the third. Whew. So that is my volume. Volume is equal to 4x to the third, and then I can do my x squareds together, so that'd be minus 90x squared plus 500x. So that's my volume. Well, we're dealing with calculus and we want to maximize something. I could graph this thing out if I wanted to, but what I'm looking for is I'm looking for the maximum value. So I'm going to take the derivative here. So I'm going to go dv dt is equal to 12x squared minus 180x plus 500. Now, good luck trying to find the maximum value without a calculator. We know that this is going to be a parabola. It's going to go up. It's going to come back down. We want to know that very top point. Now, do you guys have graphics calculators with you? Okay. Could you plug this function in? Could you plug in 12x squared minus 18x plus 500 and give me this value right here? What is this ordered pair at the very, very top? What is that? What is that value there? And I mean, I could go to Desmos and plug that into. I get the same. I should get the same value. But what is my value there? Henry, you got it? I hope I didn't make any mistakes when I was working this out. See, Caleb is typing, so I was gonna jump into Desmos and plug it in. Gives you an upward-facing parabola. Oh yeah, 12x squared. That should be negative, shouldn't it? What did I do wrong here? Minus. Oh boy, why did I put 2x squared here? That should be negative 2x. I'm just using these functions. Oh, because I multiplied through by x. So 25x minus 2x, so that would be 2x squared. That would have been right. Yeah. Yeah, because a negative parabola would open up and give me this value. Okay, well, it went this way. Okay. What did you get for a value then? Interesting. Yeah, I agree that parabola is going to open up because it's 12x. Yeah, it's going to be a minimum. What did you get for a minimum there? Yeah, we don't want a minimum though because we want the maximum value. Huh. What the heck? So I had x times 25 minus 2x times 20 minus 2x. If I multiply through here, that gives me 500x minus 50x squared. We got 821. All right, I think I have the answer on the next page. I just don't know what I did wrong. X times 20 minus 2x times 25 minus 2x. Because 2x cannot exceed 20, we have x between 0 and 10. Yeah, I get that. Huh, interesting. Henry, how did you get 821? Because that obviously is the maximum volume is 820.53 when x equals 3.68.
So on my calculator, it's an x cubed parabola. So there's actually like 3 parts. So the minimum is at 11. So it basically goes so it starts. So can I draw it? I wonder. So it looks. Can I draw?
Yeah, absolutely.
So it looks like this. So it goes all the way up here to 820.53, and then comes back down here, and then just goes straight up again.
So now, okay, I know what I did wrong. You just put it, you did not put in the derivative, did you? You
No, I
put
just put in
in,
the
okay,
I put in the original function.
I get what I did wrong. What was my derivative? Volume is equal to, it was 12x squared. What was the rest of it? Minus,
Would have been
yes, Caleb, that is exactly right. I don't know why we got the derivative. We should be finding where it crosses the x-axis. Now, you should have found one spot. It should cross twice. It should cross at 3.68, and then it's going to cross someplace farther out. Well, we know that using our diagram, we know that this x value can't be more than 20, right? Because if we cut squares more than 10, I'm sorry, the x can't be more than 10, can it? Because if we drew a square that was 10 here and we cut a square that's 10 here, there's nothing left. So that means anything over 10 or negative could not be an answer. So when we graphed out our function, and it should have been a parabola, it should have went up and it came down. No, it went the other way. Sorry about that. We're looking for where it crosses x-axis. It should cross x-axis at 3.68, and you have 11.32 also. All right. So it was the x-axis that, oh boy, not a good day for me today. Yikes. All right, does that make sense? So, Caleb, did you get the one spot that it crossed was 3.68? Now, Henry, you did it okay. It's just that you didn't use any calculus in your whole problem. You graphed out the third degree polynomial. The highest point should be the volume of that. So that's perfectly fine too. But we could have used calculus here, found the x value, and then found the value. All right. Any questions on that? It's too late to be thinking calculus right now. Yikes. All right. This is an interesting problem. This is also another maximum type problem. It says, given f of x equals 4 minus x squared, okay, so this is the parabola that is graphed out, and a rectangle is constructed with two vertices on the curve. Okay, so it means this point here and this point here is on the curve. Okay, what is the maximum perimeter of the rectangle? Oh boy, maximum perimeter. Okay, well, the first thing you have to start thinking about is, okay, this function here and these points. If you did this point here, let's just say that we went out 1, okay? So if I put 1 in here, x, this would end up being 1 squared, so 4 minus 1, that would be at 3 here, wouldn't it? Be 1 comma 3. And this value here would be negative 1 comma 3, wouldn't it? Because it would be the same distance. If you go out 3 this way, you have to go 3 backwards this way. So that means if I'm doing perimeter of this object, right, because that's what they're asking us for, what we really need to do is we need to come up with a formula for perimeter using this data. Okay, so what is, let's call this the width. What is the width of this function? Just using x as our variable, right? 2x. That is the distance here. What is the length of this thing? And it's always changing, but what is the length? F of x. And f of x is just 4 minus x squared, right? Do you agree with that? That is the height, or that is f of x. Now, the only problem that we have is that's not really perimeter, is it? Because this distance here plus this distance here plus this is perimeter. So really, for this problem, wouldn't perimeter be 4x plus, and then 4 minus x squared? Would that be the perimeter of that rectangle? Okay, so now, since I want to use calculus, I'm going to just multiply through here, so that gives me 8 minus 2x squared. So my perimeter is equal to negative 2x squared plus 4x plus 8. I want to maximize the perimeter, so I'm going to take the derivative here. It's equal to negative 4x plus 4. Could I set this equal to 0 and solve if I wanted to? So that's going to be negative 4x equals negative 4, x equals 1. So I'm going to say the perimeter is going to be a maximum when x equals 1. So let's check it out. If I put 1 in here, we already said that we had 3, so this would be 6 down here. This would be 6 up here. If I put x equals 1 here, oh, I'm sorry. This would be 1. Boy, that was not smart. All right. So if I put 1 in here for x, this is going to be 1. This is going to be 1. This whole distance, so this is going to be 2. This is going to be 2. This, if I put 1 in here, 4 minus 1 squared, that gives me 3 here and 3 here. So my maximum perimeter should be 3 plus 3 plus 2 plus 2, which is 10. 10 should be the maximum perimeter this function should have. And we could try other numbers if you wanted to. I mean, you could put other values in there, and you're going to find that this will give you the maximum perimeter. So when you're doing problems like this, what you want to do is you want to set the problem up. You want to make sure that you work the problem through. So I think I have an answer key here. So here's the answer key that they worked out. Okay. So x equals 1, so that means the perimeter has to be, the maximum perimeter has to be 10. Okay? Does that make sense? All right. This one is going to be for you guys. It says find the length and width of a rectangle that has perimeter 40 meters and a maximum area. Okay, so this one is for you. Find the length and width of a rectangle that has a perimeter of 40 meters and a maximum area. All right, I'm going to give you guys a couple minutes to work on this, and then we'll work it out. Okay? Give it a shot. See what you get. Letter A? All right. And for me, anytime you're talking about a maximum area, you always usually go to the two numbers that form a square, because that's usually the maximum area is a square of something. So if I was going to do it using calculus, it says find the length and width of a rectangle whose perimeter is 40. Well, if I did this, okay, I know my perimeter is 40. So let's say that this side is 10. So this side would be 10. No, I don't want to use 10 because then we'd get our answer right off the bat. Let's say that this side is 5. So this side would be 5. And then I would have to subtract to get the 40. That would be my perimeter, because what I'm really trying to do is I'm really trying to set up an equation, right? So that would be 15 here, and this would be 15 here, wouldn't it? So if I really wanted to set up the perimeter of 40, okay, so how could we set that up? If we let this x, okay, how can I set that up? Okay, how did you guys set it up? Or did you just know that it's going to be 10 for an answer?
Is my mic working?
It is indeed. Yep.
Oh, okay. I set it up so that y, meaning one side, was equal to 20 minus x, because if the whole thing is 40 and each side is going to be equal to its opposite, you can do 2y equals 40 minus 2x and then divide the whole thing by 2.
Okay, the only problem I see with that is now you have two variables.
Right, but if y equals 20 minus x, and then you're looking for y times x, you can plug in 20 minus x for y. So then you end up with x times 20 minus x.
All right, I've got you. Caleb, did you get that? I got it. That's exactly right. And then you're going to take the derivative, and then you take the derivative and find out what x is, and it should be 10. And that's the one thing I always look for, is I always look to make sure I keep it in one variable, because I want to make sure that, you know, I keep it in one variable. That's why if I let this side be x and this side be x, I know that it's going to be 2x, and then if I subtract, well, that would be 40 minus 2x, when it would give me my perimeter, or would give you the perimeter of that. So that's, and then take the derivative. Very nice. Excellent. Okay. How about this one? It says a farmer plans to fence a rectangular pasture adjacent to a river. Okay, so here's my river. Don't need a fence along the river. The pasture must contain 720,000 square meters in order to provide enough grass for the herd. No fencing is needed along the river. What dimensions will require the least amount of fencing? And again, this is a type of problem where, okay, I would let this be y and this would be y, so I know that they're equal. Okay, so I know that 2y, so I need to know, so I want to make it the least fencing that I can, but I know that it has to contain 720,000, so that is an area. So we know that in this problem, I know that x times y has to equal 720,000. And then I also know that 2y plus x, we want to minimize, right? We want to make it as small as possible. So then I can, you know, in this type of problem, it really doesn't matter which variable I solve for. So I can solve for y, so I can say y is equal to 720,000 over x. And then where I see y in this problem, I'm going to put 720,000 over x. So I end up with 2 times 720,000 over x plus x. So now I have an equation that I can take a derivative of. And when I find my derivative, okay, when we take the derivative of this and solve for x, we're going to come up with this value right here. Okay, so now let's take a look at this. All right, so I should have solved for x instead, because then I don't have to do 2 times 720,000. Just looking at it, it's like, but it really doesn't make a difference. So what am I going to get? 1 million. So this is going to be 1,440,000 over x, which I'm just going to make it x to the negative 1 plus x. I'm going to take the derivative of this, so that's going to give me negative 1,440,000 x to the negative second plus 1. So then I'm going to put that over x, make that x squared. Holy moly. And then we're going to set that equal to 1 or equal to 0 and solve. Bring that over, that's negative 1. Bring that x squared over. And then we'll take the square root of that, which is letter C. Was that right? I don't think I can take a, let's see, I think I can take a square root on this bad boy. I've got my TI-30 cheapo calculator here. 1, 4, 4, 0, 1, 2, 3. So that gives me, if I solve this, it gives me x equals 1,200. So that's my x value. So that means my y values have to be 600, right? Because if I just plug it back in here, y is equal to 720,000 divided by x. Well, we know x is 1,200. Boom, gives us our c value. Done. Does that make sense? Caleb? Is that okay? Interesting problems. I like being able to set them up and then solve them. All right. Here's another one. It says, find two positive numbers whose product is 186 and whose sum is a minimum. Okay, well, if I was going to start this problem, I might just do x times y is equal to 186, okay, because it said, whose product is 186, but whose sum is a minimum. Well, guess what? That means I'm going to rewrite, so I've got x plus y is a minimum. Well, I want to write it as one variable, so let's divide through by y here. So we know that x equals 186 over y. Well, guess what? I can plug that back in here. So this is going to be 186 over y plus y. I'm going to take my derivative now. Well, if I take a derivative here, again, I'm going to just rewrite this as 186y prime plus y. So, I'm sorry, that's just y to the negative 1. So if I bring that down, I get negative 186 y to the negative second plus 1. I'm going to rewrite this because I don't like having negative exponents. And then I'm going to set it equal to 0. Bring the 1 over. That gives me negative 1. Multiplied by y squared. So then if I take the square root of this, the square root of 186, oh, I guess I don't have to because they just left it like that. So y is equal to the square root of 186. And then if I plug this back in, you'll find that x is equal to the square root of 186 also. So these are called optimization problems. What you're really trying to do is you're trying to optimize, and I mean, they're all over the place. I mean, there's so many different types of optimization problems that you can have. All right, here's another one. It says, find the point on the graph closest to the point 26, 0. Okay, this is visually, this is what this problem looks like. Okay, so it says find the point on the graph of the function square root of x. Well, the square root of x looks like this, doesn't it? That is closest to the point 26, 0. Well, 26, 0 is out here someplace, right? So what you're doing is you're trying to find a point on this graph. Could be here, could be here, could be here, could be anywhere. That is closest to 26, 0. I'm going to give you guys a couple minutes to work on this and see what you get, okay? if I'm not mistaken, you're going to have to use the distance formula on this problem. I suppose you could probably use the Pythagorean theorem. I'm not 100% sure if that's going to work, because I'm looking at this, and what are we trying to do? We're trying to find the smallest distance here, right? Okay. So for me, that means I'm thinking distance formula. Okay, so we've got x2 minus x1 squared plus y2 minus y1 squared. Okay, and then I know I have a point, right? This is my point here. So I know my x1 and my x2 or y1. So I've got my point here. I've got one point. And then my other point, isn't this point going to be x comma square root of x? Wouldn't that be my second point? I'm just thinking outside the box. I haven't done this problem in a long time, but that's what I'm thinking. So this would be my x2, y2 value. I agree. I agree that it's probably going to be really hard to take the derivative. So let's just check it out. So if I put this in here, this would be 26 minus x, right? No, I'm not so sure. So this is going to be 26 minus x squared plus 0 minus square root of x squared. Okay, do you guys agree so far with the way I have it set up? Okay. Well, 26 minus x squared, let's just work that out. So I've got 26 minus x times 26 minus x. All right, get out the trusty calculator. So I've got 676 minus 26x minus 26x plus x squared. Okay, so I've got x squared minus 52x plus 676. Okay, so that is the first one. Plus, and then if I squared this, all right, so I've got 0 minus the square root of x times 0 minus the square root of x. If I did 0 through here, you get 0, 0, 0. Don't you just get x? Is my math right here? If I FOIL this out, do I just get x here? Is that right? All right. So that gives me x here. So that just gives me plus x. So now I have the square root of this, which is just x squared minus 51x plus 676. Now, this does not really matter, does it? The radical? I don't think that really matters if you're thinking about it, because it's just the derivative. So if we just take the derivative of the middle, 2x minus 51 equals 0. So if I bring the 51 over here, I get 2x equals 51, and then divide through by 2. So I think that's my x value, 51 over 2. And then to find my y value, I just plug it back into my y. I get the square root of 51 over 2. So I believe, Henry, you had it correct. It is A for the answer.
The way you did it was way simpler than the way I did it. Maybe I just did some weird stuff. Looking at it, I don't know where I went.
And I don't know. You guys both said Pythagorean theorem, and Pythagorean theorem is really the distance formula, right? Isn't it? But I don't know how I would change, because then it's like, okay, so how do you know what's changing? I'd have to look at that a little bit careful, more careful to see if that does work. It might. The Pythagorean theorem might work there, but
see what I did was I set the distance from the x plane to this point as y, and then I set the distance from the 26,0 point to the point closest to it as the distance formula, essentially, which is y squared plus 26 minus x squared. So I set that point, and then I substituted in y squared for the x squared. So I got the square root of x square root of x the square root of x squared plus 26 over 26 minus x squared. I don't know if that translates what I'm saying. And then I found the derivative of that, which contained 2 chain rules. So that's why I was saying 2 chain rules.
Yeah.
And so then I found the 0 of that, which was 51 over 2. So
the more I look at this problem, it's like, wouldn't the shortest distance have to be a right angle here? Wouldn't it have to go straight up to this thing? I mean, I don't know if it could be any shorter of a distance than a 90-degree angle straight up, because but that can't be it, because that would just be the square root of 26, wouldn't it? So obviously that's not the right answer, because I know that this is 26, 0. So if I put 26 in here, the square root of 26 is not the same thing as the square root of 51 over 2. But to me, mathematically, it seems like it would have to be a 90-degree angle there, because it just doesn't seem like it could be anything else. But I guess we did find it to be 51 over 2 and the square root of 51 over 2. So it is what it is. All right. Phew, that was a crazy problem. Last slide. You guys have a great week next week. If you get all your stuff done this week, you have all of next week off. Have a great Thanksgiving.
Thanks, Mr. Shanklin. Have a good
All
Thanksgiving.
right, see you, Henry. Bye.